Okay, the last thing we had in section 9.7 is something called Taylor's theorem. And Taylor's theorem says we had f of x is approximately f prime at c plus, f at c, f prime at c over 1 factorial times x minus c plus f double prime at c over 2 factorial x minus c squared. And you keep going, the nth derivative at c divided by n factorial x minus c to the n. That was our definition of the Taylor polynomial centered at c. So we saw on the calculator that by computing, maybe 5 or 6 terms of the Taylor polynomial, our function really became a pretty good approximation. Taylor's theorem says f of x is exactly equal to the Taylor polynomial, f at c, plus f prime at c over 1 factorial times x minus c, plus f double prime at c over 2 factorial x minus c squared, plus the nth term, plus what's known as the nth remainder. And the nth remainder is defined as it has the n plus 1 derivative at some number z divided by n plus 1 factorial times x minus c to the n plus 1. There is some number z so that the Taylor polynomial is exactly the function when you compute one more term. The bad news with this theorem is it doesn't tell you how to find the number z. And in general, there's no easy way to do that. However, what it does allow us to do is put a bound on our error. So typically this is used for the error is less than or equal to the maximum of the derivative, absolute values, divided by n plus 1 factorial x minus c to the n plus 1.
It's not f to the or f of c. Next of n plus 1.
It's the maximum of the next derivative. So we found, say we found the 4th order Taylor polynomial, it would be the maximum of the 5th derivative. Okay, so for example, yesterday we saw e to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, we'll go to 4, x to the 4th over 4 factorial. And I might ask you to find e at, I don't know, maybe negative 0.1. You could plug that in. 1 plus negative 0.1 plus negative 0.1 squared over 2 factorial plus negative 0.1 cubed over 3 factorial plus negative 0.1 to the 4th over 4 factorial. And you could grab your calculator, type that up, and get an answer. The question now is, how good is that answer? How close is that really to e to the negative 0.1? And the answer would be the error is less than or equal to. Let's see, I found the fourth order Taylor polynomial, Maclaurin polynomial. So I need to find the fifth derivative. What's the fifth derivative of e to the x? E to the x, because the derivative of e to the x is always e to the x. That's why I picked e to the x. It's a nice easy one. I need to find the maximum of that derivative between negative 0.1, which is the point I'm interested in, and the spot where I centered this polynomial. Where is this polynomial centered? It's centered at 0. So, consider the function e to the x. What's its maximum value when x can be between negative 0.1 and 0? What's the maximum value you could have for e to the x between negative 0.1 and 0? Not 0. In fact, e to the x can never be 0. It's always a positive number. Oh, did you mean plug in 0? Yeah, the maximum would happen when x equals 0. How come? What happens when you take e and you plug in negative numbers? You get smaller. How come? Well, yeah, and negative numbers force you to drop the e down to the bottom, so you're getting fractions. So the maximum value on the interval negative 0.1 to 0 is e to the 0, which is 1, times x minus c. What's x? X is 0.1. C was 0. That's where we centered it. To the fifth, since we did the fourth order polynomial, divided by 5 factorial.
Is it negative 0.1?
It is negative 0.1. Typically we put absolute values around it, though. We want error to be a positive number. So how much is 0.1 to the fifth divided by 5 factorial? Well, 5 factorial is 120. How much is 0.1 to the fifth? 1 times 10 to the negative 5. And then you divide that by 120.
8.3 repeating times 10 to the negative 8.
That's pretty low. So what that would tell me is, if I were to work this out and calculate it, I'm accurate to like 8 decimal places with only having computed 4 terms of the Taylor polynomial. So that error formula allows you to get a bound on how big of an error do you have. You could also use it the other way and say, I want to make sure that I'm accurate to 6 decimal places. If I want to be accurate to 6 decimal places, how many terms do I need to compute? So you could use it both ways.
So how far does your calculator go?
How far does the calculator go? I don't know. My guess is in the calculator, they're not using the Taylor polynomial or the Maclaurin polynomial. You got to remember, those guys lived a long, long time ago. And since then, there have been other techniques similar to these, similar to computing this sort of polynomial, but other techniques that converge much more quickly. So instead of needing 6 terms, you might only need 3 terms. So that's my guess. I don't know exactly what algorithm they use, but my guess would be it's not that. Based on that idea, though. Other questions? Okay, so that was the end of section 9.7. Now we go on to section 9.8. A power series is defined as the sum from n equals 0 to infinity of a to the n, a sub n, times x minus c to the n. In this series we would say this is centered at c. We're going to consider these power series as a function. We consider these as functions. So we're going to have f of x equals the sum from n equals 0 to infinity of a sub n times x minus c to the n. Once you have functions, you begin to talk about the domain of the function. What's the domain of a function mean? All the possible x values. In this case, what we mean by all possible x values is what x numbers can we plug in so that this infinite series will converge. That's how we're going to define the domain. Values for which the series converges. When you have a power series, there are three options for the domain. Option number one, the domain could be only the number x equals c. How come you're always guaranteed that that function will converge at x equals c? Because it makes every term 0. If x equals c, you have c minus c, that's 0. You add up a bunch of zeros, you get 0. So you're guaranteed that it will always converge at least one point. Option number two, there is a value r so that the series converges for absolute value of x minus c less than r. We're guaranteed that it converges at c, but it's possible that it might converge at more points. And if it does converge at more points, there's going to be a whole interval where it converges. R is called the radius of convergence. The third possibility is the series is absolutely convergent for all real numbers. In this case, we say the radius of convergence, the letter r, is infinity. Series converges everywhere.
Isn't that kind of like this cycle? Is that kind of like the lab? How unless I did it wrong.
Sort of, except in the lab you were dealing with integrals, not series. Same sort of idea. One of those integrals converged, and one of those integrals diverged. So same sort of idea. Sometimes for certain values our series will converge, and sometimes for certain values it will diverge, is what can happen on option number two. All right, makes a lot more sense with an example. How about the sum from n equals 0 to infinity of n factorial times x minus 2 to the n? Typical problems, I'm going to ask you to find two things. I'm going to ask you to find the radius of convergence, and I'm going to ask you to find the interval of convergence. How would you determine where that series converges and diverges? We have a long list of tests for series, for converging and diverging. I don't remember how many tests we had, 10, 11, 12, something like that. Which test do you want to use?
The ratio test.
Why do you want to use the ratio test?
There's the factorial.
Two reasons. There's a factorial. That tells you should almost always use the ratio test. The other thing is, you have something that looks kind of geometric, doesn't it? It doesn't have just a number in there. It's got an x, but that's okay. But it looks like something to a power. That's kind of a geometric term. And when did we use the ratio test? When we had factorials and when we had
The quantity times geometric.
a quantity times a geometric. So this one fits both of them in a sense. All right, so to find the convergence of these, we typically use the ratio test. We're going to have the limit as n goes to infinity. How did that ratio test work again?
A to the n plus 1 divided by
A to the n a sub n plus 1 divided by a sub n. So that means I'm going to have n plus 1 factorial times x minus 2 to the n plus 1. There's a sub n plus 1 divided by a sub n. That's n factorial x minus 2 to the n. And we had absolute values around that. And what do we need that limit to be in order for this series to converge? When did the ratio test tell you a series converged and when did it diverge? Not greater than 0. Less than 1. This series will converge when this limit is less than 1. All right, well, we do a little algebra here, a little simplifying. Limit as n goes to infinity. How can you simplify this? N plus 1 on the top. X minus 2 also on the top. I subtract my powers, n plus 1 minus n, that's the power 1. And here, n factorial goes 1 times 2 times 3 up to n, where n plus 1 factorial goes 1 times 2 times 3 up to n, and then an n plus 1. So everything cancels out but the n plus 1. I guess the only thing left on bottom is a 1. When is that limit going to be less than 1? Well, what happens as n goes to infinity? This part goes to infinity. This is, doesn't have any n's in it, does it? So when is this limit going to be less than 1? Never? Only when x is 2. Why only when x is 2? Because that'll be 0. 0 times anything is 0. This is less than 1 only when x equals 2. So that's the first case. Sometimes these converge only at one number, and that's what's happening here. So we would say converges for x equals 2. And if it asks for the radius of convergence here, we would call the radius of convergence 0. Because you can't go past the number 2 at all. The only place it converges is at the number 2. You can't go bigger, you can't go smaller. your radius is 0. Questions on that one?
So the R is the range that it could be in?
R is the range that your x values can be in. In this case, R is 0 because the only number that works is the number 2. It doesn't have any range, that's correct. Alright, let's try another one. How about the sum from n equals 0 to infinity? I'm going to start 1 to infinity on this one, because on this one I think I'm going to have x minus 3 to the n over n squared. So I better start that one at 1. I can't start it at 0 because I'd be dividing by 0, and that would be bad. Once again, I want to find the radius of convergence, and after we find the radius of convergence, we'll talk about the interval of. How do I determine the radius of convergence? Which test? Ratio test. Why ratio test? Yeah, again, this has an n in the exponent. It looks like a geometric thing. Geometric thing times something else. That tells you you'll probably want to use the ratio test. All right. Ratio test. Limit as n goes to infinity. I'm going to have x minus 3 to the n plus 1 divided by n plus 1 squared divided by x minus 3 to the n over n squared. A sub n plus 1 divided by a sub n. Flip and multiply. Limit as n goes to infinity. X minus 3 to the n plus 1 over n plus 1 squared times n squared divided by x minus 3 to the n. Simplify a little bit. That's the limit as n goes to infinity of x minus 3 times n squared over n plus 1 squared. Subtracted my exponents again. N plus 1 minus n, that gives me a 1. Once again, I need to know, when is this limit going to be less than 1? At 3, it's certainly less than 1. Because at 3, it's 0. If I plug 3 in, I get 0. Can I plug any other numbers in?
Less than 3 to be negative. Oh, no. It's actually that.
Getting close, though.
3 and 0.
Closer. Between 4 and not infinity, not negative 4. Okay, so when n goes to infinity, what happens to this piece? It's 1, isn't it? So when is this limit going to be less than 1? This limit's really going to be less than 1 when x minus 3 itself is less than 1. Because this part here, this is all the number 1 when n goes to infinity. What? That tells me one thing. First off, it tells me my radius of convergence is the number 1. What does that tell me about my interval of convergence? What numbers can I actually use for x? Less than 4? That's half correct. For example, I can't use 0. Because if I plug in 0, 0 minus 3 is negative 3. The absolute value of negative 3 is 3. 3 is not less than 1. Between 2 and 4. Why between 2 and 4? We're centered at 3. And this tells me I can go one step to the right and one step to the left. If I'm centered at 3, what's 1 to the right? 4. What's 1 to the left? 2. So we would say here our interval of convergence is, I'm going to write it this way, 2 less than x less than 4. Now my question is, we're guaranteed that this series will converge between 2 and 4. We're also guaranteed that it will diverge if we have a number x which is bigger than 4 or a number x which is smaller than 2. But what about at 2 and what about at 4? If I plug x equals 4 into that series, am I going to get a convergent series or a divergent series? Well, if I plug in x equals 4, I end up with the sum from n equals 1 to infinity of 1 to the n over n squared. So I just put 4 in. 4 minus 3 is 1. Does that series converge or diverge? Converges. How come? The limit equals 0. Absolutely true. When that limit equals 0, it tells you nothing. You need that limit to not be 0. It might converge, it might diverge, is what it tells you. It doesn't really give you an answer. Converge or diverge? Well, what's 1 to the n? What's 1 to any power? 1. So that's just 1 over n squared. What can you tell me about 1 over n squared? Converges. How come? It's a convergent p-series. P equals 2. So, I can put an equal to on the 4. I can plug in 4 and that series will still converge. What about if x equals 2? If x equals 2, I'm going to have the sum from n equals 1 to infinity. I plug 2 in. 2 minus 3 is negative 1. So I'm going to have negative 1 to the n over n squared. Does that series converge or diverge? Converges. How come?
Alternating series test. Limit up at 0.
And there's 2 parts to the alternating series test.
It's decreasing.
And it's decreasing. You could use the alternating series test to prove that that one converges. Or you could just put absolute values on it and prove that it's absolutely convergent also, because it's the same p-series that we had a minute ago. So this one is also convergent. So we can put an equal to there. Sometimes on these problems you'll have an equal to on both of these. Quite often you'll get an equal on one and not the other. And sometimes you won't get equal to on either one of those. You just have to check them individually and see if they converge or diverge. Questions on that? All right, a couple more of these. How about, so that was case number 2, where it converges on an interval. How about case number 3? Can I come up with one that converges everywhere? Sum from n equals 0 to infinity of x to the n over n factorial. I think that'll be an example of one that converges everywhere. Once again, I would use the ratio test. I'm going to have the limit as n goes to infinity, x to the n plus 1 divided by n plus 1 factorial over x to the n over n factorial. Absolute values around all that. I do my flip and multiply trick. That's the limit as n goes to infinity, x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Reduce the fractions. Limit as n goes to infinity. What do you get this time when you reduce your fractions?
X over n plus 1.
X over n plus 1. Excellent. When is that limit less than 1? Always. How come? You pick a number for x, it doesn't matter what number you pick for x, you're going to have a number on top, and it's going to infinity, you're going to have a number divided by infinity. A number divided by infinity is 0, which is always less than 1. Since that limit is always 0, which is always less than 1, when does this power series converge? Converges for all real numbers. And so in this case, our radius of convergence, we would say, is infinity. For these problems, case number 1 and case number 3 are the easy ones. Case number 1, remember, was it converged only at one point, only at 0 in this case. Case number 3 was it converges everywhere. The hard one is case number 2, where it converges on an interval, because then you also have to check the endpoints. It takes more work. All right, let me grab a good one out of the book here and see if we can find its radius of convergence.
What's the symbol for all real numbers? Is it the R?
It's usually a fancy script R, as opposed to this R. How about the sum from n equals 1 to infinity of x plus 2 to the n minus 1 divided by 3 to the n minus 1. The directions are always going to be the same. The directions are going to be find the radius of convergence and find the interval of convergence. What test do we always use to find the interval of convergence and the radius of convergence? We use the ratio test. Limit n goes to infinity. X plus 2 to the n plus 1 minus 1, which is a fancy way of saying n, divided by 3 to the n. Now, after you've done these for a while, you start to get a little lazy here, or a little quicker, and do the flip and multiply all in the same step. So here's my a sub n plus 1 term. Then I have to divide by the original. To divide by the original, I'm just going to flip and multiply, save myself a little writing. So I'm going to have 3 to the n minus 1 over x plus 2 to the n minus 1. A little quicker that way. Reduce my fraction. Limit as n goes to infinity. What do you get when you reduce this fraction? X plus 2 over 3. I subtract my exponents. N minus 1, that's 1. N minus 1 minus n, that's a negative 1, so that one goes on bottom. We want that limit to be less than 1. But notice that limit doesn't have any n's in it anymore. So what's the limit as n goes to infinity of absolute value of x plus 2 over 3? It's simply x plus 2 over 3. There's no more n's in it. So this comes down to we need x plus 2 over 3 to be less than 1. In other words, x plus 2 has to be less than 3. we were absolutely positively guaranteed that this series was going to converge at -2. Because when I plug -2 in, I get 0. Now we're told not only will it converge at -2, but where else will it converge? -1 and 0 and anything up to 1. We're not sure about 1 yet. So what's this number right here? This is our radius of convergence. So in this case, r is 3. And we're guaranteed to converge. We're centered at -2. So if I go 3 to the right, that's going to put me at -1. And if I go 3 to the left, that puts me at -5. So I'm guaranteed that that series will converge between -5 and -1.
How do you know where we're centered?
What number do I plug in to get 0 right there?
Um,
-2. That always tells you where you're centered. This is x minus -2. So it's always that number right there, x minus whatever that number is, -2. I think of it as what number do I plug in to get 0. So I'm centered at -2, and my radius is 3, which means I can go 3 steps to the right, 3 steps to the left. Now the question is,
Oh, we're centered at -2, right?
yep,
3 steps to the right is -1.
how about a positive one?
Okay.
Yes, you're right. It would be positive 1. -2 plus 3 is 1. Yes. I can do calculus instead of arithmetic. That kills me. Now, does the series converge at x equals 1? If I plug 1 in right there, if x equals 1, I had the series, the sum from n equals 1 to infinity. What do I get when I plug in 1? 1 plus 2 is 3. 3 to the n minus 1 divided by 3 to the n minus 1 is 1. Does that series converge? No, you take 1 plus 1 plus 1 plus 1, add it up an infinite number of times, do you get an answer? No, it diverges. So I cannot put an equal to sign on that one. It doesn't converge when x equals 1. How about when x equals -5? I'm going to have the sum from n equals 1 to infinity. If I plug in -5, what's -5 plus 2? -3. What's -3 to the n minus 1 divided by 3 to the n minus 1? -1 to the n. That's just -1, isn't it? Does that series converge?
Wouldn't it be alternating if you had a negative inside that?
There's no n.
It is alternating, sort of.
How come you don't have to add?
I don't know. Put the n there. There should be n. Actually, it should be n minus 1, shouldn't it be? Because when I plug in -5, I have -3 to the n minus 1 divided by 3 to the n minus 1. That's -1 to the n minus 1 times 3 to the n minus 1 divided by 3 to the n minus 1. Those reduce. It should be -1 to the n minus 1. But does that series converge? Yes? What test are you using?
Test.
The Abe test. I'm not familiar with that one. Well, let me ask you a question. What's the limit as n goes to infinity of -1 to the n minus 1? Is that limit 0? No. If that limit is not 0, what does that tell you? That the series diverges. What is that limit? What's that? What is the limit as n goes to infinity of -1 to the n minus 1?
1 or -1?
except we don't allow for two answers. You're right, this oscillates between -1 and +1. So we would say the limit does not exist. But most importantly, the limit is not 0. If the limit is not 0, the series diverges. So there's our interval of convergence. That's the best we can do. We don't get to put equal signs on either side this time. Questions on that? All right, let's try one more of those. How about, oh, that looks like a fun one. The sum from n equals 0 to infinity. -1 to the n plus 1. X minus 1 to the n plus 1. Divided by n plus 1. Lots of n plus 1s. We used our ratio test, limit, as n goes to infinity. When I put absolute values on here, what's the absolute value going to do to this -1 to the n plus 1 piece? It's just going to make it a 1. It gets rid of it. So I'm not even going to bother writing it. So I'm going to have x minus 1 to the n plus 2 divided by n plus 2. There's my a sub n plus 1 term. I flip and multiply by my a sub n term, so that's n plus 1 over x minus 1 to the n plus 1. Reduce, limit, as n goes to infinity. Looks like I'm going to have x minus 1 times n plus 1 over n plus 2. I subtract my exponents on the x minus 1s, n plus 2 minus n plus 1, that gives me a 1. Can't really do anything with that. Then what happens as n goes to infinity? It's going to converge to, this part's going to converge to 1, and so the only thing that's going to be left is x minus 1, and we need, for that series to converge, x minus 1 to be less than 1. What's our radius of convergence? 1. So r equals 1. What's our interval of convergence? 0 to 2, because I'm centered at x equals 1. I can go one step to the right, one step to the left. Check the endpoints. Which one do you want to try first? 0. If x equals 0, I have the sum from n equals 0 to infinity of minus 1 to the n plus 1 times minus 1 to the n plus 1 over n plus 1. What's minus 1 to the n plus 1 times minus 1 to the n plus 1? 1. Because minus 1 times minus 1 is 1, and then 1 to the n plus 1 is 1. So that's the sum from n equals 0 to infinity of 1 over n plus 1. Converges or diverges?
Diverges.
Diverges. How come?
Because you can compare it to 1 over n.
You can compare it to 1 over n. Which test? The limit comparison test. If I ignore that plus 1, then that series is a famous series. It's the harmonic. Does the harmonic series converge or diverge? Diverges. So you can do limit comparison test. I'm not going to write it all down. Limit comparison test with 1 over n, and you will find that that series is divergent. So I cannot put an equal to sign on the 0. Let's try x equals 2. x equals 2, I'm going to have the sum from n equals 0 to infinity of minus 1 to the n plus 1. I plug 2 in up here. 2 minus 1 is 1. 1 to the n plus 1 is 1. So I really don't need to write that down, do I? Over n plus 1. Does that series converge or diverge? Converge. How come?
Because we know the alternating harmonic series converges.
We know the alternating harmonic series converges. And again, if I cover up that plus 1, I really have the alternating harmonic series. So we assume this is going to converge. I think it would be best if we actually used the alternating series test. Does 1 over n plus 1, is that decreasing? Yes. The limit as n goes to infinity of 1 over n plus 1, is that equal to 0? Yes. So the alternating series test would tell me that that is convergent, which means I get to put an equal to sign on my interval. This one will converge for x bigger than 0, but x could be less than or equal to 2. So there's an example of you get an equal to on one of the numbers, but not the other. Nick?
Would it matter if it's like alpha? Isn't that conditionally convergent?
It is conditionally convergent at x equals 2. But it does converge. So if I plug in 2 and work that out, I am going to get a number. And that's what I care about. You're right, it is not absolutely convergent at x equals 2. But it is conditionally convergent. And that's enough. Other questions?
For these two, we always use the ratio test.
Always use the ratio test for power series. Yep. Always, always, always. Actually, we could have for this one, we made it harder than we really needed to. For that one, we could have used the root test. How come we could have used the root test? Everything's raised to the n minus 1 power. Or, even better, we could have written this way. And then we have something, the whole thing, raised to a power. We could have just said this one's geometric. And so when do geometric series converge? Geometric series converge when this ratio is between -1 and 1, which is exactly the same as saying that. So I could have skipped the ratio test on that one altogether and just said, this is geometric. It has to converge when the ratio is less than 1. That would have been the shortcut on that one. So once in a while, you could use the root test. Once in a while, you can use facts about geometric series. But every time, you can use the ratio test. So that's what most people do. Most people, by default, don't even look for the other special cases. They just jump right to ratio test, do it the same way every time. And you know you're going to get it right that way. So, safe. Other questions?